Quote, "There is something in man that makes him want to know. He looks at the world and asks questions. What is it made of? Why is it there? How does it work?" End quote, Trefil 3. Today, we will address what is it made of and how small can we get?
Is a fundamental constituent of matter observed in 1968 through deep elastic scatter. We found that protons aren't as simple as we thought. We thought they were solid particles, but they are not. Protons, in fact, are made up of 3 separate pieces. It just gets more confusing as our knowledge increases, but that is what a quark is. It's a piece of a proton, and they also make up other things, including the neutron. Oh, up, down, strange charm, top, bottom. If you don't know what a quark is, it don't matter, you still got them. And with leptons and bosons, unless something's amiss, they make up everything that we can see and that we know exists. Things made up of quarks, including protons and neutrons, are composite particles that physicists call hadrons. Many types of hadrons are theoretically described, but most exist for only very brief amounts of time. Quarks have electric charge, color, charge, mass, and spin, and having color charge means they exist solely inside of other kinds of particles and cannot exist alone, which is why quarks have never been studied on their own. Up, down, strange charm, top, bottom. If you don't know what a quark is, it don't matter, you still got them. And with leptons and bosons, unless something's amiss, they make up everything that we can see and that we know exists. Quarks can join together in 2 different ways, baryons and mesons, but most instantly decay. If a particle has 3 quarks, then it's a baryon, and if there's 1 quark and an anti-quark, then it is a meson. These tiny bits of matter are part of almost everything, and there is no unified theory to make it less confusing. But the fact that we've identified that they exist at all was so goddamn remarkable that I just sit in awe. Oh, up, down, strange charm, top, bottom. If you don't know what a quark is, it don't matter, you still got them. And with leptons and bosons, unless something's amiss, they make up everything that we can see and that we know exists.
Since Greek times, many individuals have been looking to answer the question, how small can we get? Democritus wondered what would happen if a piece of matter was split repeatedly. He came up with the theory that matter was made up of atoms, but his ideas were thrown out because Aristotle and his Hasi said that his ideas were implausible. John Dalton, English chemist and physicist, looked back at ideas of atomic theory and wondered why Aristotle shut them down so quickly. Using chemical experiments and deep thinking, he concluded that atoms are indeed the most basic particle that makes up all matter. Rutherford and Bohr were 2 individuals that worked at different times to help clear up atomic theory. They discovered that atoms are comprised of a positively charged nucleus and negatively charged electrons that orbit around the nucleus. Before moving on, we must understand that baryons and mesons are 2 types of hadrons. 2 examples of baryons are neutrons and protons. Inside of baryons are 3 quarks. Mesons are comprised of 1 quark and 1 antiquark. Strong force holds these together. Strong force is one of 4 fundamental interactions of nature. Particle accelerators are large devices that look like they should be in Star Wars. They collide charged particles at high speeds and were crucial in the discovery of the quark. Here's how they work.
Hydrogen atoms from this gas cylinder are fed at a precisely controlled rate into the fourth chamber of a linear accelerator, CERN's LINAC-2, where their electrons are stripped off to leave hydrogen nuclei. These are protons and have a positive charge, enabling them to be accelerated by an electric field. Their journey to eventually take part in ultra-high energy collisions similar to those following the Big Bang can now begin. This initial acceleration has caused LINAC-2 to be likened to the lumbering first stage of a huge rocket. By the time this packet of protons leaves Linac 2, it'll be travelling at 1/3 the speed of light. It's about to enter the booster, stage 2 of the rocket, if you will. In order to maximise the intensity of the beam, the packet is divided up into 4, one for each of the booster's rings. The magnetic force needed to keep the beams bending to the ring is so enormous that nearly 12,000 amps must flow through its electromagnets. This is achieved by making the LHC colder than outer space, so that its magnets become superconducting. Now the protons are ready to collide in the detectors. A steering magnet finally brings them onto a collision course. The total energy of 2 protons colliding in the LHC is 14 tera-electron volts and reproduces similar states to moments after the Big Bang.
The various amount of particles that came as a result of these collisions were collectively known as the particle zoo. Physicists worked to identify each particle. One in particular was Gell-Mann.
In the late 40s and early 50s, when the discovery of so-called strange particles began, I got very interested in that. But it was an offbeat field. One wasn't encouraged to work on that.
American physicist Murray Gell-Mann began to see patterns in the bewildering array of all the new members of the particle zoo. He used common characteristics to divide particles into different families. In the process, he isolated the smallest components of the atom's nucleus, the very pieces that protons and neutrons are built from.
As a theoretician, I couldn't, I suppose, really discover new things, but I could propose them. And if they turned out to be right, you could call it a discovery in a sense. What I did was to propose that the neutron and proton were not elementary, as everybody thought, but were composed instead of smaller particles called quarks, with some very bizarre properties.
Gell-Mann's quarks did for subatomic particles what the periodic table did for the chemical elements, and in 1969 he was awarded the Nobel Prize for Physics. His classification of the tiniest bits of matter brought order to the chaos of the particle zoo.
I thought that the sound, quark, was a good sound for these fundamental constituents. It sounds like a good name for the fundamental constituents of neutrons and protons. That's a quark. But I didn't know how to spell it. I thought maybe K-W-O-R-K. But then, perusing James Joyce's Finnegan's Wake, as I do once in a while, I noticed the line, 3 quarks for Mustard Mark. And I thought, 3, after all, that's a very important number for quarks. Maybe I should spell it Q-U-A-R-K.
While Gell-Mann believed quarks to be real, he never expected anyone to find one.
Some of the earliest evidence that the quark idea was correct came from experiments by friends of mine at the Stanford Linear Accelerator, in which electrons were scattered off protons. And essentially what they were doing was taking an electron microscope picture of the proton. And sure enough, there were the 3 quarks.
There are 6 quarks: up, down, charm, strange, top, and bottom. Up, charm, and top have a charge of plus 2/3. Down, strange, and bottom have a charge of minus 1/3. Each quark has its own antiparticle. For example, there are anti-up, anti-down, and anti-strange quark. Collectively, there are 12 different flavors, each regular one and each antiparticle. So, to make a baryon, 2 up quarks and 1 down quark are combined and held together by the strong force. The 2 ups both with a charge of 2/3 and the down with a charge of minus 1/3. Combined together to result in a charge of plus 1. In a neutron particle, there are 2 down quarks and 1 up quark, the 2 down having a charge of -1/3 and the up of +2/3, together canceling out. Knowing what makes up protons and neutrons is as small as we can get now, but can we go deeper? In the past, we always could, but looking at the data that we have right now, it seems almost impossible. Some physicists wonder if there may be another layer lying hidden. Only time will tell. Thank you for watching.
A quark is a fundamental constituent of matter observed in 1968 through deep elastic scatter. We found that protons aren't as simple as we thought. We thought they were solid particles, but they are not. Protons, in fact, are made up of 3 separate pieces. It just gets more confusing as our knowledge increases, but that is what a quark is. It's a piece of a proton, and they also make up other things, including a neutron. Oh, up, down, strange charm, top, bottom. If you don't know what a quark is, it don't matter. You still got them, and with leptons and